thank you very much for the reminder. I knew I'd forget that.
No problem.
Okay, it's gone past. I think probably I will start then. One or two people still drifting in, so let's see if I can get my PowerPoint. So all visible, okay. Right, it's gone past. Thank you all for joining this presentation. My name is Tim Hewson, pictured in the middle there. Probably you can see my video as well. So what I'm talking about today is ecPoint, is a post-processing tool that improves forecasts and highlights systematic model errors. This is work that's been going on for many years now. Contributors, some of the main contributors in very different ways are shown there in the list of special thanks. So I won't dwell on that, but these people have all been involved in this project in different ways. So the structure of the talk, I will talk about the history of this from when it started around about 2015, 2014, then some principles, then talk about the calibration procedure, how we produce the forecasts, examples for forecasters. There'll be a lot of examples there, but those will be gone through more quickly. Then I've done a little survey about what's going on in other organisations, so I'll show you the results of that, then some verification, and then a few bits of summary towards the end. And then in the middle, I didn't mention, there'll be a focus on systematic errors and model development, how this can be a tool with dual aims, basically. Okay, so the history of this ecPoint initiative, it was sparked by an extreme rainfall event in the Copenhagen area in August 2014, which I'll show you in a minute. Following on from that, we did a preliminary study of the viability of looking at the subgrid variability in rainfall and anticipating what that's going to be. And then together with Florian Berger, who's now my director of my department as ECMWF, we entered the Harry Otten Prize for Innovation in Meteorology. We reached the final, that was presented. The presentation related to the final was at DMS in Sofia in September 2015. I like this little picture here, so I'll show you that. That was part of the presentation where I got Florian to do some illustrations of subgrid variability on the ECMWF lawn. And then following that, we recruited Fatima Pilosu, who you saw on the previous slide, from January 2016 to work towards making this idea operational and to explore how known global model limitations could be targeted through post-processing. So it's very much, this work is in the category of expert elicitation, where we're looking at post-processing with a knowledge of what it is we're really trying to address in terms of model weaknesses, which is a bit different to perhaps some of the AI type techniques out there. Then experimental products following all this work became available in ECMWF's real-time operational system, ECCharts, in April 2019. And they are there available now for forecasters to look at, and increasingly across Europe at least, forecasters are using these. And then we had a summary of the status of that following this April release last year. Went on the Harry Otten Prize website as a little update of what had happened since the final in Sofia that I mentioned there. So to come back then to the idea or the event that triggered this work, well, there's a flash flood event in Scandinavia in August 2014. That's Copenhagen and the yellow ring there, so that's part of Denmark. And then you see in that high-res grid box, which was about 16-kilometer resolution at the time, I think, you see a massive amount of variability in the amounts of rainfall, 119 millimeters, which is probably more than has ever been recorded in one day in Reading, down to 3 on the edge of that box. So that's really showing you that the high-resolution grid box is not representative of values at points, which we kind of knew, but that kind of really brought it home to me. And this is a radar sequence, thanks to Lennart Sorth. This is a bit old now, but you get the idea that there's a lot of convection going on near to that sort of yellow ring in bands coming off the sea and so forth. And so it was basically a very convective event, which led to this large degree of subgrid variability. Synoptic pattern is shown on the top right. Yeah, you can see a low and sort of convective fronts moving through related to that, and then flooding in Malmo on the picture there. But there were flash floods in Copenhagen as well, as you'd imagine, with 110 millimeters or so. So that was the motivation. So then we can talk about the principles. Why do we want to post-process? as I've kind of said, models forecast grid box average rainfall, but most customers want point rainfall, rainfall at their house, as it were, or where they happen to be doing some activity. And as we've seen, they can be very different, especially in convective situations. And obviously, the mismatch is going to be greater and greater when you get to models with lower and lower resolution or larger horizontal resolution. So global models, ECMWF ensemble is typically, well, it's about 18-kilometer resolution now, and that's a resolution on which you will have this problem. So what we're doing is trying, with the post-processing, we're trying to convert a single value grid box average ensemble member value, or from a deterministic forecast if you wish, convert that to a probabilistic point scale forecast. So then if we combine all those ensemble member probabilistic forecasts, we get what you might call an ensemble of ensembles, and we merge all those together to give one probabilistic forecast. And that probabilistic forecast is for any pre-selected point in the given grid box. Okay. And then we can display the output as CDFs or probabilities or percentiles. The post-processing package that we have developed with Fatima and Axel in particular, that's called ecPoint. And this is a little summary of how the processing works, which I'll show in large part on the next slide. And the focus of this talk is on discussing ecPoint applied to rainfall, but the principles apply equally to other variables, albeit with some slight differences, such as 2-meter temperature, and we will be addressing that post-processing challenge in the coming months and years. Okay, so this is just to sort of summarize what we're actually doing, or what we're trying to do. So if you imagine those three boxes on the left are 3 out of the 50 ensemble members, we have an ensemble forecast value, which has a probability density of 100% in that individual ensemble member. So this is basically a forecast from one ensemble member. This is another one. This is another one. The rainfall is on the x-axis. And what we really want to do here is to convert the red line into a blue line, which is to represent the point values within the grid box. And they may be shifted to the left or to the right, in which case there is a bit of a bias correction on the ensemble mean as well, or the ensemble mean might be exactly the same. I mean, that doesn't necessarily depend on the shape, it depends on various other things. So we create all these blue lines from the red lines, and then we basically add those all together, and we end up with a final forecast over here. So this is the full ensemble forecast in PDF form. So this is perhaps the ecPoint output, and this is just a hypothetical example. The raw ensemble might be represented with this red line, and then we have the ensemble mean grid box forecast in red, and the ensemble mean from the ecPoint, which may or may not be the same, and generally it's a little bit less, as we'll see. Okay, so that's really what we're trying to do. And so the question then is, how on earth do you go about creating the format and the structure of these blue lines by which we post-process the individual ensemble member values into lots of possible point values? And the challenge is doing that so that it takes account of different types of weather where the subgrid variability will be different. So I'll illustrate that concept that the subgrid variability is different with some real cases. And so on these plots that follow, the rainfall totals are shown by rain gauges with O, high resolution model with M, or radar derived totals with R, but they all illustrate the same sort of point. And the box is a grid box of a global model. So here we have a first example. This is basically rainfall that occurred over Wales in conjunction with this deep occluding low to the south. You see the radar derived totals here, fairly uniform in around about the sort of 50mm range. These are the observed values on that occasion. That's the grid box there, so 40 to 60mm. So relatively small spatial variability with large scale rainfall, which is kind of what you would expect. However, if you have a convective situation like this, where we had showers moving in off the southwest, triggered mainly over the sea, you can see here, in a limited area model output, this is from the Met Office, there's a lot of variability in there. That's reflected, albeit not with necessarily the same values, in the radar derived totals for the same period there. So this is convective rainfall and strong winds. And what we see in these representations of truth is large variability in the totals in one dimension. And then if we have convective rainfall with light winds, so you've got strong flow here, but light flow here, what you can get is a huge amount of variability in two dimensions, because obviously the cells which form, The cells which form are not going to be moving very much or very fast. Okay, and then that's just the radar-derived tails. I didn't have it for this case, but that was another case, and we've had plenty in the recent past as well, at least in the UK. So this is convective rainfall and light winds, large variability in 2 dimensions. Okay, so the mismatch between the point and the large scale, or the point and the ensemble, will be smallest here and will be greatest here, and some intermediate value in the middle. Okay. So to reflect that, we need a calibration procedure, and we need to make our calibration procedure ideally portable so that it can be applied to easily when we change the model or to different models. So we ideally want to represent the different types of errors that we've just seen on the previous plot. So the calibration concept that we're using here is illustrated on this slide. So that's your kind of model grid on the right. The points represent the grid boxes, which is the grey grid, and then we're asking a question. We want to forecast for a particular point in a grid box. Okay, and typically in the past, going back to other methods, meteorologists and statisticians post-process numerical model output to make forecasts more accurate, and obviously this involves a previous calibration procedure, so we're following the same idea there. Typically in past work, most processing has been local. It depends on having lots of data for a particular site to calibrate with, and then you need observations and forecasts or reforecasts for the same times with the same model version. Tom Hamill in papers and book article has recommended that we need decades of data to do this properly. At the other end of the range, you've got standard historical MOS techniques, which they might use like the last 30 or 60 days, which is much more compact in terms of the model data requirement. But they tend to struggle with unusual events, and whenever the weather changes, they really struggle even more. But that's particularly true for forecasting rainfall. So if you had six weeks of dry weather, you won't really get very far with that. Anyway, so let's, instead of taking this site-specific approach, let's consider how well a model predicts rainfall or other parameters in different meteorological situations. So that's the crux of what we've done. We're thinking about the physics and the meteorology rather than actually tying ourselves to individual sites. We can define these situations on a grid box by grid box basis and a time step by time step basis, and call them grid box weather type. So these are the different meteorological scenarios. Of course, going back to the MOS techniques, model skill does also depend on location, but not because it's the latitude and longitude that's important. It's because of geographical, topographical, and solar aspects, and we can also capture those in our sort of post-processing as well. But key point here is we recognise that these type of aspects can be much the same in other parts of the world at that time or at other times of the year. So that can potentially enhance the size of your calibration data set. So this is kind of the essence of what we're doing. We're not doing local calibration, we're doing remote calibration. So let's say, for argument's sake, we want to forecast 12-hour rainfall when 700 millibar winds are expected to be light. Rainfall is predicted to be quite large scale, 5 to 50 millimeter range at a flat site in, say, Louisiana, which I just pull the place out of the hat really there. And then we ask the question, where have those types of situations as seen by the model been seen before around the world? And then you can basically see how the model's performed in those other areas, which might be these places shown here, and use that as a basis for post-processing the model forecast for that particular site. And then the idea is, because physics is universal, the errors at those sites at those times provide a good guide to the model reliability in those particular conditions shown by in green. And also then, if we sum that up over many cases over a year or so, we generate a PDF for post-processing an ensemble member when it predicts the same kind of conditions. Okay. Then you have to ask, what are the sources of errors in forecasts? Well, obviously there are random errors due to predictability, which is can be a potential problem with post-processing. But what we're trying to focus on here is factor B, which is subgrid variability, which I've already discussed. And then, of course, there are innate biases in the model, which you might think are not very big, but I'll show some evidence to the contrary. And the idea is that these are also weather situation dependent and this is on the grid box scale. Okay, so essentially we want to minimize the effect of A in what we're doing. And so we're trying to minimize that by using short range forecasts from an unperturbed control run in the calibration procedure. So typically the first 24 hours will be what we use, although we avoid a sort of spin up, the first 3 hours of spin up period, because that can be unrepresentative because of some smaller simulation issues. And then by using that, we can identify 5 statistics, B and C, in the set above. And then we assume, based on strong physical reasons and observational evidence, that B and C depend on the grid box weather type, and that may include geographical factors such as mountains and solar types as well. And that's what I illustrated on there. Okay. So when we've done all this, when we've done our kind of calibration, we've pulled all these observations for given weather types together, we can create what we call mapping functions for different grid box weather types. So this is basically a kind of like a PDF representing the values of rainfall in the grid box in a given situation. So I have some examples here of the grid box weather type mapping functions for 5 different types of weather. And to understand these are histograms which basically represent a multiplier for the model's grid box rainfall total, which allows us to get the point values. And there are large differences in these examples because the weather type which we're using to define these different weather types, or grid box weather types, they affect the subgrid variability, partly because they were chosen so to do. So to explain the histograms a bit more clearly, the white box indicates where the multiplier for the grid box rainfall is about 1. So that's where the grid box is quite accurate for point values. If the multiplier is less than 1, then the grid box total is overestimating, and where it's greater than 1, there it's underestimating. So in terms, if you're interested in flash floods, then you'd be more concerned by the size of, let's say, the yellow and the red bars than anything else. So a little reminder of the plot that I showed before. If you remember these 3 different types of subgrid variability, now I'm going to relate those to these particular charts here. So the first one on the top left is very much in the large scale rainfall category. So we see that the forecasts are quite accurate for points there. The white bar is quite big, and then the other bits tail off in a kind of Gaussian format. The second one is for the convective situation with strong winds. So here we can see there's much more subgrid variability. There's only a 10% chance that you're going to be about right with the point value. And then the third one is the convection, the slow-moving convection with light steering winds, and there you've got even more spread and the higher probability of zeros. The dark green is basically 0, I should say. Okay, and then if we think in terms of bias, which is associated with the model focus on each of these scales, then you can basically work out the average multiplying factor for each of those histograms. And so you get on the top row, the bias is around about 1 or a bit less than, but then on the 2 examples I've shown below, it's quite substantially different. So here we've got massive over prediction by the model, and here we've got under prediction by the model, and I'll come back to those later. And then if we plot what the bias is associated with all of our mapping functions, which in fact we have 214 grid box weather types at the moment, you see the distribution of the bias is shown there. So we have quite a lot of over prediction by these sort of bias correction factors. Typically sort of 70, 80, 90% is a typical over prediction ratio, but we have some scenarios in which we get under prediction as well. And those black dots refer to the cases shown on the histograms here. Okay, so we can clearly see here now we're getting to grips with the subgrid variability and also the bias. Okay, so currently the predictors that determine the weather type that we use are convective rainfall fraction, total precipitation, 700 millibар wind speed, CAPE, and clear sky 24-hour solar radiation. Without going into details, this is based on, as I said before, meteorological knowledge, expert elicitation, and they all have a significant impact on the mapping functions themselves. Typically, a mapping function in what we've done will have 8,000 data points. And so let's, for argument's sake, let's say to illustrate the true benefit of this sort of non-local calibration approach, let's imagine that we have a rare weather type in a particular location, so like high CAPE in northern Scandinavia, which might, let's say, be a 1 in 5 year event there. If you're using a MOS technique, you'd really struggle to represent that. But in the ecPoint method, because we're pooling data from all over the world, which has high CAPE situations mixed in it, it equates, if you've got 8,000 data points, to going back to about 50,000 BC. That's obviously an extreme example, but it shows the true benefit, I think, of actually pulling this data from all over the world. I mean, if you think in terms of what man was doing 50,000 BC, that's about the earliest record of any written records, I think, in the world, somewhere cave paintings from Indonesia, I believe. So we're not going to get observations, obviously, going back that far. So in terms of these predictors that we show at the top there, these are subdivided into sets using a decision tree approach. So this is where we start seeing some analogies with machine learning type techniques. This is a semi-subjectively determined decision tree. And then you can see there that we start off with all cases at the top, then we divide it up in a hierarchy for those 5 predictors. So we look at the convective fraction of rainfall first, and then we have branches here, not all the branches are shown, and then we look at the total precipitation in that particular model forecast. Sorry, that's trouble. And then the steering wind at 700 millibars, and then CAPE, and then the solar radiation, okay? And then for all these different sort of subsets, all the ends of the branches here, we have all these different types of mapping functions shown here. That's just a subset. I think that's about 1/3 of the total number. And then when we're working out, what we're doing is basically working out, when we're post-processing a forecast, what the weather types are at every grid box around the world at every time interval that we're interested in. So here we're illustrating that concept for a case over Italy, where this is a sort of synoptic chart. So we had a front dangling across the north of Italy in the Alps, and then some more troughs and convection around the low to the south. And you can see here, I mean, obviously I can't represent 214 members with 214 colours because you wouldn't know what was going on. But what I've tried to do here is just to show the convective precipitation where that's prevalent. So that's the red and the orange ones, and where it's blue, it's basically large scale precipitation. So that relates to the front, that relates to the convection with these troughs over here. And then the intensity, the actual magnitude of the rainfall forecast is shown by the darkness of the colours here. So you can see that every ensemble member has basically a set of different weather types, with obviously these relatively short range. This is T+24 to T+30. There is obviously some similarities. As you go further out, the similarities will become less with lead time. Okay, so in terms of the calibration, some of the technical details, well, we've pursued creating an open source GUI for this, using the ECMWF summer weather code over a couple of years as an avenue to do that. There's a YouTube video if you're interested in that. But anyway, the calibration for its input needs 1 year of twice daily control run forecasts up to day 2 with the current model version for all the potential predictor variables. So that's far less demanding in terms of HPC resource than creating, let's say, 20 years of reforecasts or hindcasts. So it's quite efficient in that respect. Then, of course, to go along with that, you need observations to the calibration with, such as 12-hour rainfall from gauges. We then assign all this data to a simple predefined ASCII table, and then this open source GUI, which is the subject of the summer of weather code, allows you to interactively create a decision tree. This is open source code, so anyone can use it. Create interactively a decision tree as the basis for the weather type definitions. It uses statistical tests and visual examination of histograms to define the hierarchy and the groupings, but it's all down to the user as to what those are in the end. You can preload a pre-existing decision tree to see if, let's say, a new model version has changed the mapping functions. We can have simple or complex decision tree. The decision tree can have 2 branches if you want, or you can have loads of branches and loads of leaves at the end. In principle, it can be used with any global model for different target, predictor, and variables. So it's super flexible. So that's a nice piece of software which is available on GitHub to anyone that wants it. So I'll now show you how the real-time forecast is produced. Just one slide on this. Once the calibration has been complete, of which the output are those mapping functions. So we have in CDF format, not PDF format, we have precipitation shown on the x-axis and probability to not exceed on the y-axis. And so for each ensemble member, we choose to deduce the grid box weather type, which relates to the colours you show on that Italy plot. For each ensemble member, and that defines the mapping function to apply to the rainfall forecast in that particular grid box at that particular time. So that defines the mapping function, and then we apply that mapping function to the rainfall, and we produce, it's going to come up, a little sort of CDF there. So that's the probabilistic forecast for rainfall at points in that grid box at that time. Then we merge all the CDFs, all the ensemble members produced in this way, into one CDF forecast, as I showed earlier on. This is quite a complex process. We run it in parallel on HPC, and that delivers the forecast now for 10 days in real time in about 30 to 45 minutes. And then that data can be presented to the user or the forecaster as percentiles or probabilities or CDFs. These are available at the moment. That's not available in EC charts at this point in time. And currently we do overlapping 12-hour periods up to day 10, and in project where we're doing 6-hourly periods with partners in Italy. So now some examples of how to use the products. These are illustrations of what the post-processing is actually doing with the 12-hour rainfall. Okay, so here we have on these plots, the raw ensemble is shown in red, the point rainfall distribution is shown in blue, and the bias-corrected grid box rainfall is shown in green. So in a sense, we're going from red to green to blue, but in practice, we essentially go from red directly to blue. So that's an example where longer lead times, perhaps, we don't see much difference between the point rainfall and the forecast. But on other occasions, let's say a convective situation here, we do see much bigger differences. We have a long tail, which is where a lot of the skill in creating the extremes lies. And this is an example where the bias correction has actually increased the rainfall. But it's more common for the bias correction to decrease the rainfall. And this is an extreme example of where the rainfall has been decreased a lot with some physical justification. And then you add the subgrid variability on after that. Okay, with this type of adjustment will be important for hydrologists. Where does ecPoint make a difference? Well, this is tests of statistical significance tests using the Kolmogorov-Smirnov two-sided test to show where the CDFs for the point rainfall are significantly different from the CDFs from the raw ensemble when you put the whole ensemble together. So anything is grey is dry, and we don't adjust the dry, so there's no significance to the difference there. Green is where the significance level is less than 95%, but all the orange and reds are highly significant, and this is at 99.999%. So this relatively short range, day one, we're making significant differences to the forecast all over this domain where there's any rain. A bit less so in here where we have, for example, a frontal wave. And then you see the same picture here at day 4. You see where there are frontal features where you've got large-scale rainfall is more prevalent. We're making less of a difference to the forecast, which is perfectly right and correct. And then in more convective areas, such as here in this northerly flow over Europe, the differences are very significant. And then as we go out to day 8, the significance, well, all the different synoptic patterns blur together because we've got a lot of spread in the ensemble by then, but you still see a lot of significant differences across the vast majority of the domain, and particularly in the sort of tropical convection over Central Africa there and over the Caribbean as well. So let's say a forecaster asked the question, a warning for extreme rainfall and possible flash floods. I'm going through some little forecaster type examples now. A warning may be warranted for parts of Sardinia. How can the point rainfall help me? So here we're showing, for example, the 100th percentile, which is actually the wettest ensemble member from the raw ensemble, which they might take as a plausible worst case scenario. They might say, okay, we put warnings out for the south of Sardinia. This is Sardinia here, if you didn't know. They might say put warnings out for the south of Sardinia. But when you do the post-processing with the point rainfall, basically it's saying, well, actually, no, that will be too restrictive. If you were thinking about flash floods and extreme rainfall totals, you should be putting warnings out for the majority of Sardinia, apart from the sort of northeastern area. Coincidentally, the plot for southern UK today looks a little bit like this. So you can see it's changing the area in which the forecaster would put warnings out for. Second example, this is looking at the sort of dry day scenario. The Eastern Earth ensemble is suggesting that it will rain during the day, every day this week in Reading. This seems a bit pessimistic. Can the point rainfall help me? Here we have a probability of greater 0.1 millimeters per 12 hours on day 4. This was summer last year, I think. And it's saying the chances in Reading are about 80% that it's going to rain. But if you do the post-processing, you see that the probability drops to about 40 to 50% in the Reading area. And then if we look at the same forecast over lots of different days and plot the probabilities from raw and point rainfall of getting measurable sort of 0.1 millimeters or so rainfall during the day, you'll see the point rainfall is saying don't be as pessimistic as the raw ensemble there. This forecast that I've shown was actually the Thursday one there. What actually happened? Well, we had rain on those 4 days. So overall, I mean, it's a small sample, but you'd say that the point rainfall gave better guidance, I would say, overall than the raw, which said it was going to likely to rain pretty much every day. Okay. Verification statistics globally for this kind of thing. suggests that the reliability is much, much greater in the point rainfall than it is in the raw ensemble for point values, which in a sense is reassuring and not surprising, because the raw ensemble is not trying to forecast point values, but it's good to see that it's doing the right thing. Almost perfect reliability out to day 10 there in the point rainfall. Then at the other end of the range, you're worried about extreme rainfall and flooding in Crete, let's say, but then the forecaster has seen some very jumpy forecasts from the ensemble, and would ask the question, maybe the point rainfall could help me, because the jumpy forecasts are a bit misleading. So here's an example. This is Crete shown in this picture, and you can see here the raw forecast 8 days in advance, 7, 6, 5, 4, 3, 2, 1. So here they were saying maybe, oh, we might get some heavy rain in the north. We country say no, then it's going to be in the southeast, then it's going to be in the north. But if we look at the post-processed ecPoint output for the same days, you can see basically the probabilities build up. They're always focused on the northwest of the country, much smoother, earlier signal, higher probabilities, less jumpy. And this is basically using this data with post-processing. And this is the rainfall that occurred. We don't have 12-hour rainfall totals from Crete, unfortunately, but anyway, the idea that you get is there's quite a lot of rainfall in here, up to 300 millimetres in places. The point rainfall CDF suggested 170 was possible in 12 hours. So it's not maybe underestimating things because of orographic enhancement, but it's not too far from the truth there. And certainly it would give the forecasters adequate, useful warning, I think. How does the skill of picking out occasions of 50 millimetres per 12 hours perform over the world in a 1 year of global verification? Well, the rock area is much greater for the point rainfall than it is for the raw ensemble. What's useful skill in this context? Probably it's about 0.1 above the level of skill you get from climatology. So maybe the point rainfalls is giving you skill out to about day 5 on average for this type of threshold, whereas the raw ensemble is not giving you much useful except in, let's say, really large-scale events like tropical cyclones. And then the final example, forecaster's question, is often in convective cyclonic westerly patterns in southern Norway, the raw ensemble seems to overpredict the rainfall in the mountains. So this is not good for our public forecasts or our hydropower predictions. Can the point rainfall help me? Well, the point rainfall for this case, this is southwestern Norway here. This is a synoptic pattern. If we look at the 95th percentile, normally that would be much more in the point rainfall, but here it's much less. You can see the values are lower here than they are in the raw ensemble. If we take some CDFs for that point there, you can see that the raw ensemble is shown here, then the bias corrected version of that, and then we actually have a chance of 0. And overall in the point rainfall, there's a possibility of very high totals, but overall the emphasis is very much shifted towards lower values. Okay. So this potentially could be used as a hydrological model input. And then if we delve down into this post-processing a bit more deeply and look at what the actual weather types that led to this and the kind of histograms that led to this are, we see the weather type 44210 occurring quite commonly within the ensemble. That's just our index for a particular weather type. And then you can look around the world to see where weather type 44210 actually occurred. And you can see there's quite a focus on sort of mountainous areas like southwest Norway, western Scotland here. So this is basically what it's showing is marine convection probably coming in off the sea, affecting the rainfall in this particular scenario. But I'll come back to that in a minute. But there is a physical explanation for that. So calibration can provide us with insights into the model behavior too, which nicely brings us on to section 6, systematic errors and model development. So what's the link between calibration and conditional verification? Well, subgrid variability is not a sign of systematic model error, but the grid scale biases that we're seeing, such as in that Norway example, which also depend on the grid box weather type, are mostly likely to be systematic errors, albeit with some caveats. So the calibration, which is a form of conditional verification, can identify these systematic errors. Basically what it does is correcting them for in the post-process output, and then it's defining what the errors are for the model developer. So it's dual goals here. So let's go back to that example. This is the mapping function for the weather type 44210, which was applied. And you can see here, if you remember, the green bars mean that basically we multiply the rainfall by less than 1 to produce our bias corrected grid box forecast. In fact, on average, you multiply it by 0.47. And why is that? So what's the scenario here? The weather scenario is that it's, oops, sorry. The weather scenario is that it's a high convective fraction, large totals, moderate 700 millibar winds, and low Cape. This, I think, is a key one. And what's basically happening here, we think, is that the convection scheme is triggering too readily as the air mass impinges on mountains, so the rain falls out immediately. That's how the convection scheme works. Whereas in reality, cells take time to build up and may even decay before releasing much precipitation. There's also implications of that for too much latent heat release in the model, so that's something else that needs to be borne in mind. So that's what the model's doing, which is kind of wrong. That's probably what's happening in reality. Okay. And just to advertise that ecPoint Calibrate, the calibration software allows the user using a MetView interface, which is in the container, to plot maps like that during calibration, so you can do interactive investigation of the ensemble versus observation behavior. At the other end of the scale, we've got under prediction, and again, this is an under investigated topic, the bias correction angle within the point rainfall. But what I have noticed is that the mapping functions which lead to under prediction tend to be related to convective rain less than 50%, but relatively high Cape and relatively small total. So this is maybe a sign that when we've got under prediction in the model, the IFAS is trying to generate MCS type systems with high Cape, and it's putting some of the rainfall into the dynamic category, but it's struggling. And this is actually a no model issue. We need to look more closely at that, as I say, in other geographical distributions. It's been underexplored, but that's just one little bit of an insight. And then I'm just showing you here, again, this is underexplored, but this is a plot of the bias correction of the ensemble mean. This is a May example at day 4, 5, and what I'm showing here is the point rainfall divided by the raw and the grid box scale times 100%. So it's a percentage change. So anything in the dark green and light blue is around about no bias correction. Anything in these sort of greener colours, the bias correction is removing rainfall, and these it's adding rainfall. So you can see generally in the exotropics we are removing a little bit of rainfall. In the tropics it's a real sort of mixed picture, and I just wanted to draw your attention to what's going on over Africa, where the bias correction is removing quite a lot of rainfall, whereas over South America, which you would think might be similar, we're not removing nearly as much rainfall. So that's something to investigate more thoroughly, I think, to see whether the bias correction is doing the right thing and also why it's doing that. So there's potentially a lot of avenues there to explore in the future. And then another thought I had was in terms of the subgrid variability on grid scale, certainly, let's say seasonal time scale, seasonal models, extended range. The grid boxes are very big, and you get a lot of variability in the distribution of rainfall on convective days, which you will see reflect the distribution of soil moisture underneath. So is this going to affect the evaporation? Do we misrepresent the evaporation because of this subgrid variability? As shown by those two boxes there. The evaporation is basically a very non-linear, complicated sort of process, and the fact that this is the reality and this is not suggests that maybe we have some errors to deal with there. And that's just to show that we did have a hell of a lot of subgrid variability a couple of days ago in the rainfall over the UK. Those are radar-derived totals. And then the other angle that we can use this software for is for model cycle intercomparisons. By retaining the same decision tree weather type definitions, we can compare model cycles and potentially models from different centres via the mapping function histograms. So what we've done so far, we've actually compared cycle 41R1, which is actually the high res at 16 kilometres, with the 45R1 control 18 kilometres, and there's quite a lot of model cycles in between those, but the actual histograms that we created, the mapping functions, were remarkably similar. So that suggests we don't need to really upgrade the mapping functions that we use for operational post-processing. However, now we've more recently compared 45R1 with 47R1, which is coming up at the end of June, and there are some bigger differences than we saw between these two cycles. Probably certain types of model changes have had an impact, so we will need to upgrade. And then if you want to use the calibration software, you can compare the efficacy of model changes as well. So you can focus on, let's say, the MCS type issue. Is the representation better in a new model version? And you can use the decision tree in the calibrate software. You can generate whatever sort of decision tree you like to do this kind of model investigations. And then we also have the potential in some longer term world where we could produce multi-model ensemble point forecast by doing bias correction and subgrid variability corrections for different models in different ways, and then blending all the outputs together. So how does this compare, this work? I mean, we're producing global point rainfall forecasts now routinely since April next year. What is the current status in National Met Services of post-processing? We sent 2 questions out to the main centres where global ensembles are run. We got replies from all of those, partly because I cajoled them a little bit, and then also to many other European countries in addition. Some of those replied. It's more difficult to gauge what's going on in the private sector, so I've not done that. So the first question was, does your organisation currently apply post-processing? As you can read there, I don't need to read all the words. And the answer to question 1 from all these different countries, the main ensemble producing centres are shown at the top, and some other European nations down here. Basically, very few are doing this post-processing. Japan and the USA are fairly unique at the moment. France are going to come online. USA are adjusting theirs. Canada might be thinking about it. Iceland might be thinking about it. Basically, there's very little activity going on in this area. The activity that is going on in this area is applied only basically to the countries or the surrounding areas for these, for the countries that the National Met Service is actually in. So there's not a lot ultimately to compare with. And even where the post-processing is going on in quite an active way, such as in the USA, they're trying to forecast average rainfall over a radar using a radar-derived sort of total over a 14-kilometre resolution grid box. So that's not really comparable with the point rainfall. So very few operational systems to compare with. And this is really summarising what I've said, except to highlight here, there's the representative this area initiative by Zeid Ben Bourleg and co-workers, which was published a couple of months ago. This does offer a suitable basis for comparison, albeit that he's used 24-hour totals in that study, and he's basically converting individual totals into a kind of CDF, kind of similar to what I did, except that the shapes of these CDFs are fixed for a given amplitude of rainfall, as I understand it. There's much more processing going on around the world on limited area model scales, typically 2 kilometres nowadays. This is where convection is resolved, and the techniques you need for those are very different to ecPoint. But we have compared with a couple of those, which I'll show in a minute. So here are some verification results versus in all cases against rain gauge data. So this is for ecPoint on its own. You see for 3 thresholds here, we've got a measure of the reliability of the forecast. Lower is better on here, so we've seen this one before. For small thresholds, we're almost perfect. For higher thresholds, we improve the forecast, although the improvement is not quite as good for the very high thresholds in terms of reliability as it is for the very low thresholds. Then the area under the rock curve tells you your discrimination ability, picking up these events at points. And again, higher is better on here. So again, we're already starting off from quite a high baseline here, but we're adding some value. And then for the high thresholds, we saw this before, we're adding quite a lot of value in terms of the rock area. The rock area plots are actually shown there, but I'll zoom in on one for 12 to 24-hour lead for the 50mm threshold, just to show you what's going on in terms of the details. So the point rainfall is shown by the blue, and so the 1%, 2%, 3%, 4% probability points are up here. So the skill gain is very much in the tail of the distribution, the wet tail. And that's not really surprising there, because it couldn't really be anywhere else. And this is just a little example of flash flood case that I looked at over Wales a while back. You don't want the probability for this event of this extreme total in here to be more than 2%, really, because then it will be unreliable. So the skill lying in the tails, that's exactly where it should lie. Okay. And then I looked at Zeid's paper and the results they have for small totals and large totals, not completely comparable to what we've done, but overall what he found and quotes in the paper was that they improved the reliability for small totals, but the area under the rock curve was unchanged. And for larger totals, in his case 20mm in 24 hours, they didn't improve the reliability, but they did improve the area under the rock curve. So that was improving some aspects, whereas the point rainfall is improving all aspects to varying degrees, I would say. Okay. Then if we look at limited area model systems, excuse me, we've got a couple of comparisons here. Stefan Omri visited ECMWF in February before the lockdown and uses GEMOS techniques, looking at comparing with the performance of ecPoint with the Cosmo limited area model ensemble that they use there. using the method described there. That goes out to day 10, and then we've got a comparison over Italy with another Cosmo version using a method that's based on some work done at Reading University. Okay, so for the Switzerland case, here we're showing different error metrics here. So this is a continuous rank probability skill score, and this shows the relative difference compared to the skill score of ecPoint over 10 months of verification. If you apply global EMOS to ecPoint, you make the ecPoint worse, which is suggesting that probably the ecPoint is pretty good and can't be improved on by standard, simpler statistical methods. And if you apply global EMOS to Cosmo, you end up with a forecast which is also worse than ecePoint. And if you do a blended product, if you give 30% weight to Cosmo, then you probably get the best overall forecast. When you apply the global EMOS to the Cosmo, this is the ROC curves shown for Cosmo E in black, and then the post-processed Cosmo in blue. So you see here that basically for large thresholds, the global EMOS is not improving the tail of the distribution, whereas the ecPoint is improving the tails, as we saw, and that's why we're not seeing such brilliant results, I think, from the Cosmo E post-processing. These were his conclusions. Time is short, so I won't go into great detail, except to say that the optimal weight that he found was about 30% for Cosmo E for most lead times when you're blending with ecPoint over Switzerland. As I say, global EMOS is probably suffering from a poor representation of the tails. Two reasons for this, well, one reason for this, the fact that the GMOS only has really two inputs, which is the ensemble mean precipitation and the standard deviation, whereas we're looking at all sorts of variations in the actual distribution around the ensemble forecast using 306 inputs. So we allow for variability in the actual distributions for individual ensemble members. Okay. In the comparison over Italy, this is scale selective neighborhood post-processing. That's designed to basically retain, this is the limit area model post-processing technique illustrated here. That's basically designed to retain signals in the limit area model where they're reliable and to sort of smooth them out where they're not. So random popcorn convection, maybe you've got that over the sea here, we end up smoothing that out, but we retain the topographically forced rainfall here. So this is just a comparison of the 95th percentile before and after post-processing. Okay. And the verification of 12 months verification around Italy all looks very positive, I would say, for ecPoint. The ROC area for thresholds of 20 millimeters in 6 hours. ecPoint looks very good there. That's the red one. The post-process does improving on the Cosmo Raw. If you look at March, April, May, similar sort of results. If you look at June, July, August, the area under the curve, we see here the benefit of the Cosmo Raw model, the Cosmo post-process, because the Cosmo model is able to continue the convection into the evening, which this is for 18 to 24 UTC, whereas the eSIM relief model and indeed the post-processing are not able to deal with that. So here we see a particular benefit of having the high resolution model. Okay. And there's some reliability scores up there, which are, again, reliability is good if it's lower. So again, ecPoint reliability is better for that particular threshold. But I won't go into the top right plot in the time. So ongoing projects, we've got the Mistral and Highlander projects. Mistral is the results that I've just shown come from that. We're doing 6-hour point rainfall. We've got solar radiation and orography used as additional parameters compared to the 5 that I showed before, trying to help with the diurnal cycle. And then we do the LAM ensemble post-processing, which I've shown, and blend the two together. And then the Highlander project is now underway. We're looking in that more at longer lead time forecasts, extended ranges. We'll do a 24-hour point rainfall for that. We'll also do 2-meter temperature post-processing using ecPoint, and we'll produce a new Era 5 Base 3 analysis product, which will be 70 years of probabilistic global point rainfall, which you'll all be able to use in due course. Okay. Limitations. So this list could be quite long, as could the list of future work. The validity of the forecast obviously depends on the calibration. We've seen how using worldwide data considerably helps to cover many possible outcomes. But if you have global extreme data, such as from a slow-moving tropical cyclone, maybe you're better off using the raw ensemble anyway, because we don't have calibration data for that type of scenario. Orographic enhancement and rain shadow, we've worked on that. and we put something on that topic in the 6-hour Mistral product, but there's much more work to be done on there, so that's one weaker area. The diurnal cycle errors I showed you with the Italy example. Inland propagation of sea temperature triggered convection. Again, we have done some work on that, but not finalised that. Short-lived rainfall when you can't measure it. If you can't measure it, you can't really calibrate it for. And then there's a grid packing issue as well. And then another big issue is that when we don't actually post-process a dry forecast to give any sort of rainfall, and we do have cases when rain is observed when dry is actually forecast. And the reason for not being able to do that is because we use this forecast error ratio, this multiplication factor. So loads of avenues for possible future work, lots of different parameters we could look at, such as Corfidi vectors, which are supposed to indicate the degree to which cells will move, convective cells will move, and obviously if they're going to stay in one place for a long time, then you'll expect extreme rainfall. Diurnal cycle, for the dry convection, we could add a branch to the decision tree using, let's say, for zero rain, and then use lightning forecast as the main predictor. With other predictors as well. That would have to be additive, not multiplicative. So that will basically allow you to add rain where the model is producing none if lightning was diagnosed. And this is something that people in, well, forecasters basically have complained about. We could examine globally the impact of cities on rainfall using the population density or derivatives related to the wind. We would like to put CDF plots and EC charts. Targeted investigations of bias correction, which I mentioned, hydrological applications we could use as a cheap downscaler for climate projections if we ran the climate model, maybe from ERA5 reanalysis for the calibration. We could use more crowdsourced data for calibration, and here we've used expert elicitation, what you might call real intelligence rather than artificial intelligence to drive this work. I'm sure there are avenues for AI and machine learning to improve the techniques and the predictions, but I would like to retain the facility to always deconstruct the post-process CDFs to allow us to understand why the forecast has been adjusted, because without that, I don't view that is particularly useful. We want to go through a data governance process to make the grid files widely available. There's 4 possible parameters in that. Again, I won't go into that in detail, but if you keep the video later, you can have a look at that. But we need WMO sanction headers for these new products. And we're working on that at the moment. And then finally, to summarize, because I'm out of time, new products became available in April 2019. To address the subgrid variability problem. They can be displayed in different ways. I gave you some nice examples, hopefully, of how that can help you. They correct for subgrid variability and biases, depends on grid box weather type. We've got a novel calibration procedure using worldwide data to increase the sample size massively. We had examples of forecaster examples, different types of ends of the range. We saw very positive results of verification, including better results or competitive results, which are competitive compared to limited area models. Limitations have been highlighted, some are being worked on. There's a paper on arXiv which is being revised for the journal. If you want to type that in Google, you'll find it. And then future work will continue in the EU-funded projects, Mistral and Highlander and any others that we happen to create. And then just to finally say, there was a quote from yesterday I had from Neil Armstrong, hopefully he doesn't mind me quoting this. He said he's found these to be really useful in highlighting the areas most at risk and for communicating a reasonable worst case scenario. And then just to highlight that the ecPoint forecasts, of course, it's not just a new thing to compete with models. It will be nothing without the high quality ECRF ensemble data that drives them. And that's all I have to say. So thank you very much. So I will try and go onto my other screen and have a look at if there's any comments or questions. So if you'd like to maybe raise your hand or add some comments in the chat. I see we have quite a lot of comments here already, so maybe I will deal with the ones that are in the chat first. So Magdalena says, thanks Tim, very good work. 2 questions. Can ecPoint be applied to reanalysis as well as to estimate the CDF of the precipitation? Yes, that's work which will go on in Highlander, as I mentioned at the end. Yes, it will fill the observation gaps. And ecPoint can be applied to the reforecast, that's true. But the trouble with the reforecast is that we never really kind of get a whole year's worth at the same time. So that's why we have a separate sort of control run to do the calibration with. But in principle it can, but the ecMLF reforecast strategy does not really make that sensible at the moment. Estie's kind of answered that, which I've only just seen, so sorry about that. So hi Mark Linder in Switzerland. He says, have you thought about taking into account the spread of the ensemble to further improve on the reliability? That's an interesting question. I think innately that is taken into account. Perhaps that's something that we should maybe discuss offline if you have a particular idea, but I kind of think that is really already taken into account in the member by member post-processing. And then Hans from the reanalysis team was asked, does ecPoint compare better to GPCP than the raw ecMLF model does? I have not looked at GPCP at all. Okay, so he says GPCP is wetter in the global mean. I think no, I think basically we would reduce the actual global mean. So no, it does not. It will reduce the global mean somewhat compared to the raw ensemble. I should add, though, that a lot of the rainfall falls over the sea, and I guess GPCP, I'm not sure if GPCP includes data over the sea. And strictly the post-processing we've done, although we've produced data over the sea, is not necessarily valid over the sea. I mean, it produces nice continuous plots. So that's certainly the GPCP comparison is something to look at and think about more directly. And then Peter Dubel has asked, it would be easy to extend the amount of training data by using gridded precipitation observation for training such as had UK grid instead of using local gauge observations. Do you see any problem doing this? Well, I think there is a problem because that's not going to be available over the whole world, and it will be incompatible with the data that we do have from all over the world, which is sign-up observation. So we really wanted to focus on using sign-ups which are applicable everywhere and really do represent the point rainfall. I don't know exactly what had UK grid, the grid size of that is. If it's very small grid, let's say 1 or 2 kilometers, then it's probably analogous to point rainfall. But then, is it fully valid on those scales? So I think I'd be reluctant to sort of suddenly throw a massive amount of data just from the UK in, because it might skew the results against other parts of the world. So Tim Palmer would like to ask a question. So Tim, can you unmute yourself and ask the question?
Hi Tim, can you hear me?
Yes.
Can you hear me? Yes, good. Okay. Yeah, sorry, for some reason I can't raise my hand. I think the version I've got of Teams is not old enough or not new enough to allow me to do that or something. Anyway, it doesn't matter. I just want to say, I think, sorry, this is more of a comment than a question, but I think this is an absolutely fantastic piece of work you've done, and it's really, you know, radically transformed the usefulness and indeed the skill and all the rest of it, reliability. And, you know, I hope this is the start of something, you know, big and important. However, I just wanted to, you know, when I was at ecMWF, it was kind of the, I don't know if it was written or unwritten, but there's certainly a kind of a feeling that post-processing was the work of member states and not of ecMWF. And it seems to me that your work highlights two things. One is that, you know, this to an ensemble is a complicated business, and you've shown quite a lot of very sophisticated code that has done this calibration and downscaling. And secondly, you know, as you say, from all over the world to calibrate, you know, a region. And so for me, it kind of completely puts the sort of, you know, the nail in the coffin that it's that one can really just do all this post-processing, you know, on a regional basis. It's something that has to be done, I think, at the centres like ecMWF that produce these global forecasts. So I guess my question is there any kind of discussion? I'm thinking more at the management level rather than sort of research level about whether this is now a kind of a change in ecMWF, that the production of these kind of calibrated forecasts is as integral a part of ECMWF's research as indeed developing the models and data assimilation systems.
Yeah, I mean, I think it's a growth area. It's something that we've sort of tread carefully with to try and not annoy people. And I think we've had positive feedback from a lot of member states now about the usefulness of this and asking for us to do this more. And so we sort of tread carefully. Thank you very much for all your positive comments. That's really appreciated. I'm possibly saying that it's the nail in the coffin for local post-processing is a bit strong, because there are a lot of people doing post-processing on limited area models in their own sort of local areas. And maybe if they're using slightly different techniques, they will come with better results than the ones I showed for Switzerland and Italy. And also some of those post-processing techniques avail themselves of the local sort of gridded radar-derived totals that are available in, let's say, Germany and the US and so forth. And so some of those techniques, in terms of representing things like orographic rainfall, will certainly do better than the ecPoint value. And I've not sort of gone into that in great detail because we didn't have any particular evidence, but I'm pretty certain that orographic enhancement, if you've got decent radar derived totals in that area, you'll do a bit better with some of those aspects. So I don't think it's a nailing of the coffin for the post-processing techniques around the world, but I think it's certainly a very competitive broad scale alternative, which I'd like to see lots more people use and adopt. And in terms of ECMWF policy, like I say, well, we're just sort of treading carefully, and we've had positive feedback so far. And I think if we can show that it's a way of also actually improving the model for the member states and our customers as well, then it will its use in future will be allowed to grow. You said a lot. Hopefully I've more or less answered your points there. Do you want to come back with anything?
No, I don't. But just to say, you mentioned about AI. I mean, there are some interesting sort of stochastic downscale also coming out of this generative adversarial network theory, which I think may be of interest as well. So I mean, it's a kind of clearly a growth area, this, I think.
Yeah,
and a very important,
you have to look at the machine learning
one too
as well. Yeah, sure. Okay, thank you very much. Okay, so I'll go back to the list. Peter Watson has asked if there's any potential for doing temporal downscaling as well. I don't know if Peter, would you like to come online and explain that a little bit more?
Yeah, sure. Sorry, I was just kind of meaning, you know, you're producing results, as I understand it, for like 6 hourly rainfall. But if you wanted, say, 1 hourly or 3 hourly totals, could this approach also be used if, say, you had observations, you know, with samples of rainfall, that kind of temporal resolution?
Yeah,
given weather types.
In principle, yes, but we do the calibration process when if you got down to 1 hourly totals will be a little bit more hit and miss. Let's say we have little timing errors in the rainfall and the convection scheme. Yes, I think it becomes more complicated at 1 hour timescale. 3 may be possible. I think in terms of getting global data for 1 and 3 hourly calibration, that's going to be quite a challenge, really. The principle, I mean, we use the 6 and 12 hour. We say this is useful for flash flood prediction because basically if you've got extreme totals and it's a convective situation, a forecaster knows that that's not going to be rainfall spread over a long period. It's most likely to come in extreme bursts like we've had over the UK in recent days. So I think maybe the applications that are a bit more limited unless you're going into the nowcasting regime, which I'm not really.
Okay, thanks.
Okay, and then Hans says, to clarify a point he made earlier on, no, ecMWF is wetter. Yeah, okay, so ecPoint is basically making ecMWF forecast drier, so they perhaps would agree with the global average of DPCP better, but we need to do that in a quantitative way. Then Federico Cutrara has asked, could this be applied to regional model? Well, in principle, you can apply it to any sort of model, but as I say, when you get down to very fine scales, in terms of space and time, then the calibration procedure is not so accurate or efficient, I would say. And I think there are other, like the neighborhood post-processing that we talked about, which was developed in the Mistral team. That's a more viable option, albeit maybe combined with some bias correction as well. So I think for regional models, generally different types of post-processing are more appropriate because they have convection resolved within them. Sue Gray has asked if can I apply ecPoint to fields other than precipitation. Yes, I think temperature is very viable, maybe other things like cloud cover. Sue has said about wind gusts. I think wind gusts is, mean wind, I would say, is problematic. And I don't think the ecPoint will be good for mean wind because that's very dependent on topography. So I'm working on another project with some people in Germany on downscaling the wind forecasts. So we then have a point versions of everything maybe at some future point. But for wind gusts, it's sort of, yeah, I think the main problem with doing that, I think, would be actually the wind gust data, which reporting wind gusts around the world, that system is in a complete mess. So I think that would be our biggest issue, and the local geographical variations are another problem on top of that. So I think probably that's not viable at this point in time. So Tayadat from France, I guess, I don't know, says, thanks a lot, Tim. Have you investigated the frequency biases of ecPoint versus raw ensemble? Yeah, that should have been shown to some degree in the reliability diagrams. We've also done some telegram diagrams which show going from a U-shape to a very flat shape. That's in an earlier sort of newsletter article in the ECMRF newsletter. Hopefully that's what you mean with that question. Would you like to amplify that with a comment over the mic? I think we have a problem with that. I can't hear you, I'm sorry. Okay, we'll move on. So Adrian Guest, is there any capability in using machine learning or deep learning architectures to improve the ensemble mean prediction? I'm sure there is potential of using these AI type techniques. And people are working on that kind of thing. And I don't know that much about machine learning. It's something which I need to get up to speed on. But I think there would be indeed. Whether it would be competitive or not, maybe it would beat this. I don't know. But, okay, I think we're well past time now. It's 20 to 12. The questions have run out. People are leaving the conversation. So thank you very much, everyone, for listening. Hope it was reasonably clear. It's quite disconcerting when you present, when you can't see the audience, but I appreciate all the questions and comments, and have a nice day. Okay, cheerio.